The European Space Agency's automated transfer vehicle has a crucial role in maintaining human spaceflight operations on the International Space Station, humanity's permanent outpost in space. Each ATV is named after a scientist or individual who fundamentally changed the way in which we understand the universe. And this series of films aims to examine these scientific breakthroughs and visionary concepts that made history. As a visionary and dreamer, Jules Verne helped inspire a new generation of inventors and scientists to make their aspirations of space exploration a reality. Born in 1828 in the French town of Nantes, Verne's love for all matters nautical led him to speculate on explorations beyond the realm of 19th century experience in his Voyage Extraordinaire, a sequence of 54 novels which included the possibilities of sailing the seas of space. The fourth book in the series, De la Terre à la Lune, From the Earth to the Moon, focused on the challenges of launching 3 intrepid explorers using a cannon across 400,000 kilometres of space, with the ultimate goal of landing on the moon. Verne's solution to the problem of how to dispatch his heroic explorers to their celestial target involved an exploration of how objects fired with a single massive initial impulse would behave in gravitational fields, the science of ballistics. Of the 4 fundamental forces of nature, including the strong nuclear, electromagnetic and weak nuclear, gravity, the mysterious force of attraction exerted by all masses on each other, is the weakest. But it's the one that ultimately determines the large-scale structure of the universe. So what does Newton's equation for gravity tell us? The force of gravitational attraction between the spacecraft, there, and I, here, is less than 1/100,000th of a Newton. So it's hardly surprising that most of the tiny attractive forces exerted by everything around us in our everyday lives are overwhelmed by the force of Earth's gravitational attraction on us. And that's what we know as our weight. In my case, nearly 900 newtons. Gravity is a force that, in spite of many misconceptions, certainly exists in space. Using Newton's equation, we can actually calculate that raising an apple from the surface of the Earth to the altitude of the International Space Station, ISS, only reduces its weight by around 10%. Gravitational forces actually extend to infinity, following an inverse square law and diminishing with distance, but never completely disappearing. So why do objects in the space station appear to be weightless? It's because the station and everything on it are constantly falling towards the Earth, accelerating, because of gravity, at the same rate. They are, in fact, all on a path that follows the curvature of the Earth. Newton first modelled this idea in 1728 by imagining a cannon on top of a very high mountain, a cannon which fires a ball horizontally. The cannonball will follow a curved path, a ballistic trajectory, and we can also see that if the correct horizontal velocity is imparted to the cannonball, it will follow a curved path which precisely matches the curvature of the Earth's surface. The ball would be in orbit, in a state of constant free fall. Now, since gravitational fields accelerate all masses equally, if the cannonball was hollow, then all the occupants inside will be following exactly the same path with no relative motion between them. Replace the idea of a hollow orbital cannonball with the International Space Station and the result? Everything on the station appears to float, but they're actually constantly falling. So what are the implications of gravity for Vern's cannon? An object fired at an angle with an initial velocity will follow a ballistic trajectory in a gravity field. It's a curved path that we call a parabola. Now, if we discount the effect of atmospheric drag to simplify the modelling, the precise shape of the trajectory and how far it finally ascends ultimately depends, for a given gravity field, on its launch velocity and its initial angle. As the object follows this ballistic path upwards, its kinetic energy will reduce, converting into potential energy as it works against the gravitational force of the Earth trying to pull it downwards. Although not a physicist, Verne correctly calculated that an object fired from Earth with a velocity of 11 kilometres per second, that's a speed that would take us from London to Paris in less than 35 seconds, such an object would have the capability of reaching the Moon. Verne's solution of how to impart this colossal initial speed to the spacecraft carrying his explorers was the construction of a giant gun barrel, the Columbiad, 270 metres long and 18 metres in external diameter. Verne's explorers would ride in a 20-ton hollow projectile just under 3 metres in diameter, to which the Columbiad would impart the velocity needed to fire it to the Moon in a single giant blast. The exploits of Verne's fictional heroes captured the imagination of the general public and scientists alike. But although his works inspired many, more detailed analyses of his proposed method highlighted its limitations. Within 10 years of Verne's publication, the father of Russian rocketry, Konstantin Tsiolkovsky, recognized that the Columbiad would produce a crushing acceleration, many thousands of times that due to Earth's gravity, and hundreds of times higher than that endured by any astronaut. This would have resulted in the deaths and possible literal flattening of the occupants. Yet he was sufficiently inspired to begin his own speculations on how to make such a voyage survivable and practical. His solution? An inverted cannon on which the projectile itself was mounted. Now, instead of a short, powerful blast, Tsiolkovsky's cannon would have a much longer burn time. In the case of a ground cannon firing, the projectile is fired upwards, with the entire cannon structure recoiling in the opposite direction. But in Tsiolkovsky's design, gases are expelled downwards and the entire vehicle recoils upwards. The extended burn spreads out the time over which the momentum changes. In Tsiolkovsky's design, the change of momentum is spread out over a much longer period of time, thus reducing the resulting accelerations to survivable values. Now, any human occupants would experience the discomfort of a few times their effective weight for as long as the engines are firing, but this is much better than the crush of 1,000 G acceleration produced by Verne's proposed Columbiad gun barrel. The empty rocket stages are discarded once used to minimise dead weight and maximise the effective engine thrust. And in this way, inspired by Verne, Tsiolkovsky paved the engineering pathway for multi-stage rocket acceleration to whatever target and velocity would be required, whether to voyage to the Moon or, closer to home, to rendezvous with a space station orbiting the Earth. ATV, ESA's automated transfer vehicle, relied on precisely these rocketry principles to carry out its mission in delivering essential cargo to the International Space Station. ATV is launched from Kourou, Europe's spaceport in South America. The 760-ton Ariane expels thousands of kilograms of exhaust gases every second at supersonic speed, powering ATV upwards to an initial orbital altitude of over 250 kilometres and a velocity approaching 8 kilometres per second. From this orbit, ATV will use its own propulsion and guidance systems to close in on the station. The entire launch sequence from Kourou to low Earth orbit takes less than 10 minutes, a spectacular engineering testament to the inspirational vision of Jules Verne.